The James Webb Space Telescope looked too deep into space. It pointed its golden mirrors at the darkest corners of the cosmos, at places where nothing should exist. And what it found there has left scientists stunned. The universe, it seems, is filled with impossible things. Galaxies that should not be, stars that form too quickly, light that traveled from a time when there should have been only darkness. If you enjoy exploring the mysteries of the cosmos, please take a moment to like this video and subscribe to the channel. Your support helps us continue this journey through the stars together. Now, let us drift deeper into this beautiful mystery. Far above the clouds of Earth, beyond the reach of city lights and the haze of our atmosphere, there floats a machine unlike any other. It does not roar or rumble. It makes no sound at all. It simply hangs there, in the cold silence of space, watching, waiting, listening to light that has traveled for billions of years just to reach its golden face. This machine is the James Webb Space Telescope, and it is, without question, the most powerful eye humanity has ever turned toward the heavens. Picture a mirror, not a small one, like the kind you might find in a bathroom or a hallway. No, this mirror is enormous. It stretches more than 20 feet across, wider than many houses. But it is not a single sheet of glass. Instead, it is made of 18 smaller mirrors, each one shaped like a hexagon, like the cells in a honeycomb. Together, they form a great golden flower, blooming in the darkness of space. That golden color is not just for show. Each mirror is coated with a thin layer of pure gold, less than 1,000th of the thickness of a human hair. Gold, you see, is very good at reflecting a special kind of light. Not the light we see with our eyes, something different, something older. The telescope lives about 1 million miles from Earth. That is roughly 4 times farther than the Moon. At that distance, our entire planet would look like a small blue marble, barely visible against the endless black. The telescope chose this lonely spot for a very good reason. Out there, away from the warmth and glow of our world, it is incredibly cold. And cold is exactly what this telescope needs. You might wonder why a telescope would want to be cold. Think of it this way. When you look at the night sky, you are trying to see very faint, very distant things. Any extra light, any extra warmth, makes that job harder. It is like trying to hear a whisper in a noisy room. The quieter the room, the easier it is to hear. The Webb telescope searches for a special kind of light called infrared. We cannot see infrared with our eyes, but we can feel it. It is the warmth you feel when you stand near a fire or step into sunshine. Everything warm gives off infrared light. Your body does. Your coffee cup does. Even the telescope itself does. This is the challenge. If the telescope is warm, it blinds itself with its own infrared glow. It would be like trying to photograph the stars while holding a flashlight pointed at your camera. So the telescope must be cold. Very, very cold. Colder than anything you have ever experienced. Colder than the coldest winter night. Colder than the freezing point of air itself. To stay cold, the telescope carries a sun shield. This is not a small umbrella. It is a vast sail, about the size of a tennis court, made of 5 thin layers of special material. Each layer is thinner than a human hair. Together, they block the heat from the sun, the earth, and even the moon. On the sunny side of the shield, temperatures can reach over 200 degrees. On the dark side, where the mirrors hide, it drops to nearly 400 degrees below zero. In that frozen shadow, the telescope can listen. It can hear the faintest whispers of ancient light. Light that started its journey when the universe was young, when the first stars were just beginning to flicker into existence. But getting the telescope to its distant home was no simple task. This machine was too large to fit inside any rocket in its final form. The mirrors were too wide. The sunshield was too big. So the engineers had to fold it up, like a giant piece of origami, and tuck it inside the nose cone of a rocket. On Christmas morning in the year 2021, that rocket lifted off from a launch pad in South America. It rose through the clouds, through the atmosphere, and into the blackness of space. Inside, the telescope waited in darkness, folded tight, beginning its long journey outward. Over the next 2 weeks, something remarkable happened. Slowly, carefully, the telescope began to unfold. First, the solar panel spread its wings to catch the sunlight and power the spacecraft. Then, the sunshield began to stretch out, layer by layer, like a butterfly emerging from its cocoon. Finally, the great golden mirror unfolded, segment by segment, locking into place with perfect precision. There were over 300 things that could have gone wrong during this process. 300 moments where a single failure could have ended the mission. Engineers around the world held their breath, watching their screens, waiting for each step to complete. And one by one, each step succeeded. The telescope opened its eyes. For the next few months, the telescope drifted toward its final destination, that cold and quiet spot 1 million miles away. As it traveled, engineers back on Earth adjusted the mirrors, tilting each hexagonal segment by tiny amounts, aligning them until they worked together as one perfect surface. The adjustments were so small they could not be seen with the naked eye. Yet they made all the difference. Finally, the telescope was ready. Ready to look backward through time. Ready to see things no human eye had ever seen. Ready to search for the first light. Here is something wonderful about the universe. When you look at something far away, you are also looking at something old. Light takes time to travel. The light from our sun takes about 8 minutes to reach us. So when you look at the sun, you are seeing it as it was 8 minutes ago. The nearest star beyond our sun is so far away that its light takes more than 4 years to reach us. When you look at that star, you are seeing it as it was 4 years in the past. The farther you look, the deeper into history you see. This is what makes the Webb telescope so special. It can see so far that it looks back billions of years. It can see galaxies as they were when the universe was only a few 100 million years old. To put that in perspective, the universe is now about 13.8 billion years old. Those early galaxies existed when the cosmos was less than 5% of its current age. It would be like looking at a photograph of a person who is now 80 years old, but the photo was taken when they were only 4. But there is a problem. The universe has been expanding ever since the Big Bang. Everything is moving away from everything else. As space expands, it stretches the light traveling through it. The light gets pulled, like taffy, into longer and longer waves. Light that started as visible blue or white gets stretched into red, and then beyond red, into infrared. This is why the telescope looks at infrared light. The oldest light in the universe, the light from those first stars and galaxies, has been stretched by the expansion of space. By the time it reaches us, it has shifted into infrared. If we want to see the earliest chapters of cosmic history, we must look in infrared. And that is exactly what the Webb telescope was built to do. Now, scientists had ideas about what those early galaxies should look like. Based on our understanding of how the universe works, based on decades of observations and calculations, they made predictions. Young galaxies, they thought, should be small. They should be messy. They should be dim. After all, it takes time to build a galaxy. You cannot just snap your fingers and create hundreds of billions of stars. You need gravity to pull gas together. You need that gas to collapse and ignite into stars. You need those stars to live and die and spread heavier elements into space. You need second and third generations of stars to form from that enriched material. All of this takes time. Lots of time. So the earliest galaxies, the ones that existed just a few 100 million years after the Big Bang, should have been in the baby stages of this process. Small nurseries of stars, just beginning their long journey toward becoming the grand spiral and elliptical galaxies we see closer to home. That was the expectation. That was what the model said. And then the Webb telescope opened its eyes and looked. What it found shook the foundations of astronomy. One of the first images the telescope produced was a deep field image. This is a technique astronomers use to see the faintest and most distant objects. The telescope stares at a single tiny patch of sky, gathering light for many hours, building up an image pixel by pixel. The patch of sky is incredibly small, about the size of a grain of sand held at arm's length. Yet within that tiny window, the telescope found thousands of galaxies. Some of these galaxies were relatively nearby, their light having traveled only a few billion years. But others were incredibly distant. Their light had been traveling for almost the entire age of the universe. And these distant galaxies, the ancient ones, looked wrong. They were not small. They were not dim. They were not messy collections of baby stars. Instead, some of them were enormous, bright, fully formed. They looked like mature, well-developed galaxies, the kind that should take billions of years to build. Scientists gave them a name. They called them universe breakers. Think of it this way. Imagine you walk into a hospital nursery, a room full of newborn babies. You expect to see tiny infants, just a few pounds each, wrapped in blankets, unable to walk or talk. But when you open the door, you find some of the cribs contain fully grown adults. Tall, strong, completely developed. That would be impossible. Adults do not appear in nurseries. They have to grow up first. It takes years. Yet here were these galaxies, impossibly mature, existing at a time when the universe itself was barely a toddler. How could this be? How could these ancient galaxies have grown so large so quickly? The math did not work. There had not been enough time. Not according to our understanding of physics, not according to our models of galaxy formation. Something was wrong. Either our observations were mistaken, or our understanding of the universe was incomplete. Scientists scrambled to double-check the data. Perhaps the measurements were off. Perhaps the distances were wrong. Perhaps these galaxies were not as old as they appeared. Calculating the distance to a faraway galaxy is tricky business. It involves studying the light very carefully, looking at how much it has been stretched by the expansion of space. Small errors in this measurement could lead to big errors in the calculated distance and age, but the data held up. The observations were confirmed. These galaxies really were where they appeared to be, shining brightly at a time when they should have been faint smudges at best. The scientific community buzzed with excitement and confusion. Papers were published. Conferences were held. Debates raged in journals and on social media. Some astronomers wondered if the Big Bang theory itself was wrong. Others suggested tweaks to our understanding of dark matter and dark energy. Still others proposed that the very first stars were different from what we had imagined. Perhaps much larger and brighter, capable of building galaxies more quickly. We do not yet have answers. We have mysteries. And in science, mysteries are not failures. They are invitations. They are signposts pointing toward deeper truths, waiting to be discovered. Let us drift now into the story of how we got here. How did humanity come to build such a telescope? How did we reach the point where we could see light from the edge of time? The story begins, as so many stories do, with curiosity. Human beings have always looked up at the night sky and wondered, what are those points of light? How far away are they? What lies beyond what we can see? For most of human history, we could only wonder. Our eyes were our only instruments. We mapped the stars, gave them names, wove them into myths and legends. We noticed that some lights moved against the backdrop of fixed stars, and we called them planets, from an ancient word meaning wanderers. We watched the moon go through its phases and the sun rise and set, but the true nature of these celestial objects remained hidden. Then, about 400 years ago, something changed. A man named Galileo Galilei pointed a small tube with curved glass lenses at the night sky. It was a simple device, a crude telescope by today's standards. But what he saw through that tube changed everything. He saw that the moon was not a perfect sphere, but a world with mountains and craters. He saw that Jupiter had moons of its own, tiny points of light circling the giant planet. He saw that Venus went through phases like our moon, proof that it orbited the sun. He saw that the Milky Way, that hazy band across the sky, was made of countless individual stars, too many to count. These observations cracked open the door to a new understanding of the cosmos. Earth was not the center of everything. The universe was far larger and more complex than anyone had imagined. And with better tools, we could learn more. Over the centuries, telescopes grew larger and more powerful. Astronomers built great observatories on mountaintops, away from city lights and atmospheric distortion. They replaced glass lenses with mirrors, which could be made larger and more precise. They invented new ways to record light, first with photographs, then with electronic sensors that could detect even the faintest glows. In the 20th century, telescopes moved into space. The atmosphere, while necessary for life, is a nuisance for astronomy. It bends and blurs the light from stars. It absorbs certain wavelengths completely. No matter how good your telescope is, if it sits on the ground, it looks at the universe through a shimmering, hazy window. Space, telescopes solve this problem. Above the atmosphere, the view is crystal clear. The stars do not twinkle. The images are sharp. And wavelengths of light that never reach the ground, absorbed by the air, can finally be seen. The most famous space telescope is probably the Hubble Space Telescope. Launched in 1990, Hubble showed us the universe in breathtaking detail. It revealed galaxies colliding, stars being born, nebulae glowing with spectacular colors. Its images became icons, posters on bedroom walls, desktop backgrounds, symbols of our cosmic curiosity. But Hubble had limitations. It saw mostly visible light, the same kind our eyes detect. It could see some infrared, but not the deep infrared needed to peer back to the earliest epochs of the universe. To see that far, to see that old, we needed something new. The idea for the Webb telescope was born in the late 1980s, even before Hubble launched. Scientists knew that eventually we would need a larger telescope, optimized for infrared, capable of seeing the first light in the universe. They began to plan. They began to dream. The project took decades. It faced budget overruns and schedule delays. There were moments when it seemed the telescope might never fly. But scientists and engineers persisted. They solved problem after problem. They invented new technologies. They tested and retested every component. And finally, on that Christmas morning in 2021, their creation took flight. A generation of work, riding a pillar of flame into the sky, carrying with it the hopes and curiosity of all humanity. Now, let us return to those impossible galaxies. Let us sit with this mystery for a while, turning it over in our minds like a smooth stone found on a beach. The universe, according to our best theories, began about 13.8 billion years ago in an event we call the Big Bang. This was not an explosion in space. It was an explosion of space itself. Before the Big Bang, there was no space, no time, nothing we would recognize as reality. Then, in an instant, everything began. In the first moments, the universe was unimaginably hot and dense. There were no stars, no galaxies, no planets, just a seething soup of energy and particles expanding and cooling. As minutes passed, some of those particles combined to form simple atoms, mostly hydrogen and helium. But the universe was still too hot for anything larger to form. It was a glowing fog, opaque with light. Hundreds of thousands of years went by. The universe continued to expand and cool. Eventually, it cooled enough for the fog to clear. Light was finally free to travel. This is the oldest light we can see, the cosmic microwave background, a faint glow that fills all of space, a baby picture of the universe when it was only about 380,000 years old. But there were still no stars. The universe had entered what scientists call the cosmic dark ages. There was matter, mostly hydrogen gas, drifting in vast clouds. There was gravity, slowly pulling those clouds together. But there was no light, no sources of illumination, just darkness and waiting. Then, somewhere in that darkness, something stirred. A cloud of gas grew dense enough that its core collapsed under its own weight. The pressure and temperature at the center rose until, finally, nuclear fusion ignited. The first star was born. We call these first stars population 3 stars, though we have never seen one directly. They were probably giants, hundreds of times more massive than our sun, burning hot and bright. They lived fast and died young, exploding as supernovas, scattering heavy elements into the surrounding space. These first stars lit up the darkness. Their light began to travel outward, stretching as it went, shifting from visible to infrared as the universe expanded. When the Webb telescope looks at the most distant galaxies, it is searching for the descendants of those first stars, the light from cosmic dawn. But the impossible galaxies pose a challenge to this story. If galaxies need billions of years to grow large, how did these ancient galaxies get so big so fast? The universe at that time was only a few 100 million years old. That is a long time by human standards, but it is a blink of an eye in cosmic terms. Several possible explanations have been proposed. Let us consider a few. One possibility is that we have underestimated how quickly stars can form. Perhaps in the early universe conditions were different. The gas was purer, mostly hydrogen and helium, without the heavier elements that slow down star formation today. Perhaps gravity worked more efficiently on these pristine clouds, pulling them together faster, igniting more stars in less time. If stars formed more quickly, galaxies could grow more quickly too. The impossible galaxies might not be impossible at all. They might simply be products of an era when the universe was a more efficient star factory. Another possibility involves dark matter. Dark matter is a mysterious substance that makes up most of the matter in the universe. We cannot see it directly. It does not emit light or interact with light. But we know it exists because we can see its gravitational effects. Galaxies rotate faster than they should based on their visible matter alone. Something invisible is adding extra mass, extra gravity. In the early universe, dark matter formed vast webs and filaments, pulling ordinary matter along with it. Galaxies formed at the nodes of this cosmic web, where dark matter was densest. Perhaps dark matter clumped together more quickly or more densely than our models predicted. Perhaps this gave galaxies a head start, allowing them to grow larger faster. There is also the question of how we measure the masses of these ancient galaxies. When we look at a distant galaxy, we cannot put it on a scale. We have to infer its mass from its brightness. Brighter usually means more stars, which usually means more mass. But what if some of those early galaxies had black holes at their centers? Black holes that were actively feeding on surrounding gas. When a black hole consumes matter, the matter heats up and glows brilliantly before it disappears beyond the event horizon. A single black hole can outshine an entire galaxy of stars. If the impossible galaxies contain such active black holes, they might appear brighter than they really are. Their true masses might be smaller than we first estimated. They might not be universe breakers after all, just universe tricksters. These are all hypotheses, ideas waiting to be tested. The beauty of science is that it is self-correcting. When observations contradict expectations, we do not throw up our hands and give up. We investigate. We propose new ideas. We design new experiments and make new observations. Slowly, piece by piece, we approach the truth. The Webb telescope continues to observe. Every day it gathers more data, more light from the distant cosmos. With each new image, our picture of the early universe becomes clearer. The mystery of the impossible galaxies may one day be solved. Or it may lead to even deeper mysteries, questions we have not yet thought to ask. For now, let us simply sit with the wonder of it all. Let us appreciate the fact that we, tiny creatures on a small planet orbiting an ordinary star, have built a machine capable of seeing the light from the beginning of time. We have stretched our vision across billions of years, across unimaginable distances, to glimpse the infancy of the cosmos. The universe is stranger than we imagined. It is also more beautiful, and there is so much more to discover. As we drift through this narrative together, let us pause to consider what it means to look back in time. We do it so casually, pointing our telescopes at the sky, that we might forget how remarkable it truly is. When you look at the night sky, you are not seeing the present, you are seeing the past. Every star, every galaxy, every point of light is a time capsule, a message sent long ago, finally arriving at your eyes. The light from nearby stars shows them as they were years ago. The light from distant galaxies shows them as they were billions of years ago. In a sense, the night sky is a history book. The farther you look, the earlier the chapter you are reading. And the Webb telescope can read chapters that no other telescope could access, chapters from the very first pages of the cosmic story. But there is a limit. There is a distance beyond which we cannot see, not because our telescopes are not powerful enough, but because the light has not had time to reach us. The universe is only so old. Light can only travel so fast. There is a boundary, a horizon, beyond which lies the unobservable. We call it the observable universe, and it is the bubble of space from which light has had time to reach us since the Big Bang. Beyond that horizon, there is more universe. How much more? We do not know. It might extend forever in all directions. It might loop back on itself like the surface of a sphere. It might contain other bubbles of space with different properties, different laws of physics, different histories. We simply do not know. What we do know is that within our observable bubble, there are roughly 2 trillion galaxies. 2 trillion. That number is almost impossible to grasp. If you counted one galaxy per second, it would take you 60,000 years to count them all. And each galaxy contains hundreds of billions of stars. The scale is beyond human intuition. And yet, here we are, little beings on a little world, managing to comprehend at least a piece of this vastness. We have equations that describe the expansion of space. We have theories that predict the behavior of matter and energy across cosmic time. We have telescopes that turn the invisible into the visible, the distant into the near. The impossible galaxies remind us how much we still have to learn, but they also remind us how far we have come. A few centuries ago, we did not even know that other galaxies existed. We thought the Milky Way was the entire universe. Now we know there are trillions of galaxies, and we have photographed some of them as they appeared when the cosmos was young. This is the journey of science. It is humbling and exhilarating in equal measure. Every answer opens new questions. Every discovery reveals how much remains hidden. And that is not a reason for despair. It is a reason for hope. There will always be more to explore. The universe will never run out of mysteries. Let us drift a little further now, into the details of what the Webb telescope has shown us. One of the telescope's signature achievements is its ability to see through dust. Throughout the universe, clouds of gas and dust block visible light. These clouds are stellar nurseries, places where new stars are being born. But because the dust blocks visible light, telescopes like Hubble could not see inside them. They saw only dark silhouettes against brighter backgrounds. Infrared light is different. It passes through dust the way radio waves pass through walls. The Webb telescope, with its infrared eyes, can peer inside these dusty nurseries and watch stars being born. The images are stunning. Pillars of gas, light years tall, with baby stars glowing at their tips. Swirling disks of material around young stars, the same kind of disks that planets form from. Shockwaves and jets of material streaming out from newborn stellar systems. One famous region the telescope observed is called the Carina Nebula. This is a vast cloud of gas and dust located about 7,000 light-years from Earth. Hubble had photographed it before, revealing beautiful structures carved by the radiation of hot young stars. But Webb showed it in a whole new light, literally. Details hidden behind veils of dust suddenly appeared. The cosmic cliff, a wall of gas at the edge of a stellar nursery, revealed intricate textures and structures invisible before. Another stunning image came from a nearby galaxy called the Cartwheel Galaxy. This galaxy is the result of a cosmic collision. Long ago, a smaller galaxy plunged through its center, like a stone dropped into a pond. The result was a ring of star formation spreading outward, a wave of creation triggered by destruction. Hubble had seen the general shape, but Webb revealed the fine details, individual star-forming regions, the composition of the gas, the structure of the colliding galaxies. These images are not just pretty pictures. They contain data. Scientists analyze the light to determine what elements are present, how hot the gas is, how fast things are moving. Every image tells a story written in the language of light. The telescope has also turned its attention to planets beyond our solar system. These are called exoplanets, worlds orbiting other stars. We know of thousands of exoplanets now, discovered by various methods over the past few decades. Some are gas giants like Jupiter. Some are rocky worlds like Earth. Some orbit in the habitable zone of their stars, where liquid, water might exist on their surfaces. But knowing a planet exists is different from knowing what it is like. To learn about an exoplanet's atmosphere, we need to analyze its light, and that is very hard because exoplanets are incredibly faint compared to their parent stars. It is like trying to see a firefly next to a searchlight. The Webb telescope has special instruments designed for this task. One technique is called transmission spectroscopy. When a planet passes in front of its star, a tiny amount of starlight filters through the planet's atmosphere on its way to us. Different gases absorb different wavelengths of light. By analyzing which wavelengths are missing from the starlight, we can determine what gases are present in the planet's atmosphere. The telescope has used this technique to study several exoplanets. It has detected water vapor in the atmospheres of some. It has found evidence of carbon dioxide in others. These are important molecules, building blocks for the kind of chemistry we associate with life. One particularly intriguing target is a planet called K2 18b. This world is about twice the size of Earth and orbits in the habitable zone of a small red star. Using Webb data, scientists detected signs of carbon-bearing molecules in its atmosphere, including possible hints of dimethyl sulfide, a molecule that on Earth is produced primarily by living organisms. Does this mean there is life on K2-18b? Not necessarily. We need more observations and more analysis. The detection is uncertain and other explanations are possible. But it demonstrates the power of the telescope. For the first time, we have a tool capable of sniffing the atmospheres of potentially habitable worlds, searching for the chemical fingerprints of life. The search for life beyond Earth is one of humanity's oldest and deepest questions. Are we alone? Is life common in the universe? Or are we a rare accident? The Webb telescope brings us closer to answering this question than ever before. It cannot tell us definitively whether alien life exists, but it can tell us whether the conditions for life exist in other places. And with each new observation, the picture becomes clearer. Beyond exoplanets, the telescope has studied objects in our own solar system. It has observed Mars, capturing infrared images that reveal details about the planet's atmosphere and surface composition. It has studied the giant planets, Jupiter and Saturn, watching storms rage in their atmospheres and examining the composition of their clouds. One particularly beautiful target was Neptune. The Webb telescope captured images of this distant ice giant, showing its rings with remarkable clarity. Neptune's rings are faint, made of dark material that is hard to see. The last detailed images of them came from the Voyager 2 spacecraft, which flew past in 1989. The Webb images showed the rings in a new light, along with many of Neptune's moons, tiny points of light orbiting the blue-green world. The telescope has also observed smaller objects, asteroids and comets, that drift through the solar system. These objects are remnants from the formation of the planets, frozen time capsules containing material billions of years old. By studying their composition, we can learn about the raw ingredients that built our solar system, the same ingredients that ultimately came together to form Earth and everything on it, including us. There is something poetic about using a telescope designed to see the distant universe to study our own cosmic neighborhood. The same instrument that peers back to the dawn of time can also examine the worlds next door. It reminds us that the universe is continuous, a single fabric of space and time stretching from here to the edge of the observable cosmos. Let us now return to the impossible galaxies and consider what their existence might mean for our understanding of the universe. The Big Bang theory is one of the most successful theories in all of science. It explains an enormous amount of observational evidence. The expansion of the universe, first discovered in the 1920s, is consistent with a universe that began in a hot, dense state and has been expanding ever since. The cosmic microwave background, that ancient glow, left over from when the universe was young, matches the predictions of Big Bang theory with remarkable precision. The relative abundances of hydrogen, helium, and other light elements in the universe match what Big Bang nucleosynthesis predicts. All of this evidence has convinced the vast majority of scientists that the Big Bang theory is fundamentally correct. The universe did have a beginning. It has been expanding and evolving for nearly 14 billion years. The structures we see today, galaxies, stars, planets, grew from tiny fluctuations in the early universe, amplified by gravity over cosmic time. But no theory is ever complete. The Big Bang theory does not explain everything. It does not explain why the universe began. It does not explain what, if anything, came before. It does not explain certain fine-tuning problems, such as why the universe is so flat and uniform on large scales. To address these issues, scientists have proposed additional ideas like cosmic inflation, a brief period of exponential expansion in the first fraction of a second. The impossible galaxies may be pointing to another gap in our understanding. Perhaps the early universe was more dynamic than we thought. Perhaps some process we have not yet discovered accelerated the formation of the first galaxies. Perhaps our models of star formation need revision. Perhaps dark matter behaves differently than we assumed. Some scientists have proposed more radical ideas. What if the Big Bang theory itself needs modification? What if the universe is not quite as old as we think? What if the expansion rate has changed over time in ways we have not accounted for? One alternative that occasionally gets attention is called the tired light hypothesis. This idea suggests that the redshift we observe in distant galaxies is not caused by the expansion of space, but by light losing energy as it travels. If light gets tired on its journey, becoming redder over time, then distant galaxies would appear redshifted even in a static universe. However, the tired light hypothesis has serious problems. It cannot explain the cosmic microwave background. It cannot explain the time dilation we observe in distant supernovas, where explosions appear to occur more slowly because the universe was smaller when their light began traveling. It conflicts with many other lines of evidence that support the expanding universe model. Most scientists consider it thoroughly ruled out. Another idea that has gained some attention is early dark energy. In the standard model of cosmology, dark energy is a mysterious force that is accelerating the expansion of the universe today. We discovered this acceleration in the late 1990s by studying distant supernovas. Dark energy seems to act like a constant energy density in empty space, a cosmological constant that pushes the universe apart. But what if dark energy was stronger in the early universe? What if there was an extra burst of dark energy shortly after the Big Bang, which then faded away? This early dark energy could have affected how quickly structures formed, potentially allowing galaxies to grow larger faster. It is a speculative idea, but it is the kind of thing scientists are exploring as they try to make sense of the new observations. Then there is the question of black holes. The early universe may have been seeded with black holes from the very beginning. These are called primordial black holes, hypothetical objects that could have formed from density fluctuations in the first moments after the Big Bang, before any stars existed. If primordial black holes exist, they could have acted as seeds for galaxy formation. Gas would fall onto them, feeding them, causing them to grow. The energy released by this feeding process could have triggered star formation in the surrounding gas. Perhaps the impossible galaxies grew so quickly because they had a head start, built around primordial black hole cores. We do not know if primordial black holes exist. We have not detected them directly. But their existence is not ruled out by current observations. They remain an intriguing possibility. The point is that the impossible galaxies have opened a door. They have shown us that our picture of the early universe is incomplete. They invite us to think more creatively, to consider possibilities we had not taken seriously before. This is how science advances. Observations drive theory. When the data surprises us, we must revise our ideas to accommodate it. And that is a wonderful thing. Science is not about defending old ideas at all costs. It is about following the evidence wherever it leads, even if it leads to uncomfortable places, even if it overturns cherished beliefs. The universe does not care what we think it should look like. It simply is what it is. Our job is to observe it carefully and adjust our understanding accordingly. As the Webb telescope continues its mission, gathering more data from the early universe, we will learn more about these impossible galaxies. Are they truly as massive as they appear? Or have we made errors in our measurements? Do they contain supermassive black holes that boost their brightness? Were conditions in the early universe genuinely different from what we expected? These questions will take years to answer. Science moves slowly, carefully, checking and rechecking. But that slowness is a feature, not a bug. It ensures that when we do reach conclusions, they are built on solid foundations. The impossible galaxies are not going anywhere. They will still be there, frozen in time by the light that left them billions of years ago, waiting patiently for us to understand them. Let us drift now into some of the specific discoveries the telescope has made about these ancient galaxies. One of the most extreme examples is a galaxy nicknamed Maisie's Galaxy, named after the daughter of one of the astronomers who discovered it. When first spotted, its light appeared to come from a time only about 390 million years after the Big Bang. That would make it one of the most distant galaxies ever observed, shining when the universe was less than 3% of its current age. Further analysis revised the distance estimate slightly. The galaxy is now thought to be from about 390 million years after the Big Bang, still incredibly early. What makes Maisie's Galaxy remarkable is not just its distance but its size. It appears to be about half the size of our own Milky Way, a substantial galaxy by any measure. Think about what that means. The Milky Way is a mature galaxy containing roughly 200 billion stars. It has been building itself for over 13 billion years, accreting smaller galaxies, forming new stars from gas clouds, slowly growing to its current grandeur. Maisie's Galaxy achieved comparable size in just a few 100 million years. The difference in growth rate is staggering. Another surprising discovery came from a galaxy called Glas ZZ13. When first identified, it appeared to be even more distant than Maisie's Galaxy, potentially from just 300 million years after the Big Bang. If confirmed at that distance, it would be one of the earliest galaxies ever seen, a beacon of light from the cosmic dawn. These early galaxies have another peculiar feature. Many of them appear to be producing stars at a furious rate, far faster than galaxies in the more recent universe. Star formation rate is measured in solar masses per year. Essentially, how much mass is being converted into new stars each year. A typical modern galaxy like the Milky Way forms a few new stars per year. Some of these early galaxies appear to be forming hundreds of solar masses worth of stars per year, a rate 100 times higher. Such rapid star formation is hard to sustain. Stars need raw material, hydrogen and helium gas. Forming stars at such a high rate would consume gas quickly. Either these galaxies had enormous reservoirs of gas, or they were particularly efficient at turning gas into stars, or our measurements are off. There is also the puzzle of supermassive black holes. At the center of almost every large galaxy in the local universe sits a supermassive black hole, a black hole millions or billions of times the mass of the Sun. Our own Milky Way has one, though it is relatively modest, only about 4 million solar masses. These black holes did not just appear. They grew over time, consuming gas and merging with other black holes. Building a supermassive black hole takes time, just like building a galaxy. You start with smaller black holes, perhaps formed from the deaths of massive stars, and grow them through accretion and mergers. But the Webb telescope has found evidence of supermassive black holes in some of those early galaxies, black holes that appear far too large for their age. How did they grow so quickly? Did they start from unusually large seeds? Perhaps the remnants of the first generation of supermassive stars? Did they grow through rapid accretion in the gas-rich early universe? Did they form through some entirely different mechanism we have not yet imagined? These questions about black holes are closely related to the questions about galaxy sizes. Black holes and galaxies seem to grow together. Their masses correlated in a way that suggests their fates are intertwined. If we can understand how the earliest black holes formed and grew, we might also understand how the earliest galaxies formed and grew. One particularly remarkable object is a galaxy that hosts an active black hole, meaning a black hole that is actively consuming matter and releasing tremendous amounts of energy. This galaxy, observed at a redshift indicating it comes from less than 500 million years after the Big Bang, contains a black hole with a mass of about 10 million suns. That is already impressive. But what is more striking is the ratio of the black hole mass to the galaxy mass. Normally, a supermassive black hole is about 1,000th the mass of its host galaxy. In this early universe example, the black hole is a much larger fraction of the total, suggesting it grew exceptionally quickly relative to the stars around it. These observations are still preliminary. More data is needed. More careful analysis is required. But the pattern is consistent. The early universe appears to have been a more extreme place than we expected, a time of rapid growth and intense activity, a cosmic construction boom that built galaxies and black holes at a pace we struggle to explain. As we consider these findings, let us also reflect on the people who make this science possible. The Webb telescope is a machine, but it was built by humans. Thousands of engineers, scientists, technicians, and administrators worked for decades to bring it to life. They came from countries around the world, united by a shared curiosity about the cosmos. Behind every discovery is a story of human effort. Long nights spent debugging software, painstaking work aligning mirrors to nanometer precision, years of testing and retesting to ensure nothing would fail in the hostile environment of space. The people who built this telescope may never see their names in headlines, but their fingerprints are on every image it produces. And there are the scientists who analyze the data, who spend long hours staring at computer screens, writing code, checking calculations. They ask questions, form hypotheses, debate with colleagues. They experience the thrill of discovery and the frustration of dead ends. They are human beings, driven by the same curiosity that led Galileo to point his crude telescope at the moon 4 centuries ago. This is the human story of science. It is not just about facts and figures. It is about the wonder that drives us to explore, the patience required to understand, the humility to accept when we are wrong. The impossible galaxies are not just challenges to our theories. They are gifts, reminders that the universe is vaster and stranger than we imagined. invitations to continue the journey. And so, we drift onward into deeper mysteries, guided by the golden eye of the Webb telescope. One thing the telescope has revealed with particular clarity is the structure of galaxies in the early universe. Modern galaxies come in several basic shapes. Spiral galaxies, like our Milky Way, have pinwheel arms of stars and gas swirling around a central bulge. Elliptical galaxies are more blob-like, smooth collections of older stars with little ongoing star formation. Irregular galaxies have no particular shape, often the result of gravitational disturbances or collisions. Scientists long wondered what shape the first galaxies would have. Would they look like the spiral and elliptical galaxies we see today, or would they be something else entirely? The Webb telescope has begun to answer this question. Many early galaxies appear to be neither spiral nor elliptical. They are clumpy, irregular collections of star-forming regions, bright knots scattered across a diffuse glow. This makes sense. In the early universe, there had not been enough time for gravitational interactions to smooth things out, to gather stars into orderly patterns. The galaxies were still young, still settling into their eventual shapes. Some early galaxies do show hints of structure, perhaps the beginnings of disks or even early spiral arms. These observations suggest that galaxy structure can develop surprisingly quickly, at least in some cases. It is another piece of the puzzle, another constraint on our theories of how galaxies form and evolve. The telescope has also captured images of galaxy interactions in the early universe. Galaxies do not exist in isolation. They clump together in groups and clusters, bound by gravity. When galaxies pass near each other, their gravitational pull can distort their shapes, trigger bursts of star formation, and even merge them into single larger galaxies. In the local universe, galaxy mergers are relatively common. We can see pairs of galaxies in the process of colliding, their stars and gas swirling together. Our own Milky Way is on a collision course with the nearby Andromeda galaxy, though the merger will not happen for another 4 billion years. In the early universe, mergers should have been even more common. The universe was smaller and denser. Galaxies were closer together. Collisions and mergers should have been frequent events. The Webb telescope has found evidence supporting this picture. It has observed pairs of galaxies in the early universe that appear to be interacting, their shapes distorted by gravitational forces. Some of these interactions may have contributed to the rapid growth of the impossible galaxies. When two galaxies merge, their gas collides and compresses, triggering intense bursts of star formation. A galaxy that experienced multiple mergers early in its life could have grown much faster than one that evolved in isolation. This merger-driven growth is one possible explanation for the impossible galaxies. Perhaps they were not impossible at all, just exceptionally hungry, growing quickly by devouring their neighbors. But mergers alone may not be enough to explain everything. Some of the early galaxies appear too large and too uniform to be merger products. They look like single coherent systems, not the chaotic aftermath of multiple collisions. So mergers are likely part of the story, but not the whole story. Let us pause here and take a breath. We have traveled far, from the launch of the telescope to its orbit around the Sun, from the first images to the impossible galaxies, from theories of the Big Bang to speculations about primordial black holes. It is a lot to take in, and that is okay. The universe does not demand that we understand it all at once. It is patient. It will wait for us to catch up. In moments like this, it can help to step back and appreciate the bigger picture. We are creatures made of atoms forged in the hearts of stars. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it was created in stellar furnaces billions of years ago. When those stars died, they scattered their atoms into space, where they eventually gathered into clouds, collapsed into new stars and planets, and ultimately assembled into living beings capable of wondering about their origins. We are the universe looking at itself. When you gaze at the stars, you are looking at your ancestors, the cosmic generations that came before, the processes that made your existence possible. And when the Webb telescope looks at the earliest galaxies, it is tracing that ancestry further back than ever before, searching for the very first chapters of a story that eventually led to us. This is not just science. It is a kind of pilgrimage, a journey to our origins. And like all pilgrimages, it is as much about the journey as the destination. The telescope has also given us new insights into the chemistry of the early universe. Stars are not just sources of light. They are factories. Inside their cores, nuclear fusion transforms lighter elements into heavier ones. Hydrogen becomes helium. Helium becomes carbon and oxygen. In the most massive stars, the process continues all the way to iron. And when those stars explode as supernovas, they scatter these elements into space, enriching the cosmos with the building blocks of planets and life. The first generation of stars had none of these heavier elements to work with. They formed from pure hydrogen and helium, the only elements that existed after the Big Bang. This primordial composition made them different from stars today. Without heavier elements to help cool and fragment the gas clouds, the first stars were probably much more massive than typical modern stars. Some may have been hundreds of times the mass of our Sun, blazing with intense light before exploding after just a few million years. These first supernovas began the process of enrichment. They sprinkled the universe with carbon, oxygen, nitrogen, and other elements. The next generation of stars formed from slightly enriched gas. They lived, died, and spread even more heavy elements. Generation after generation, the universe became chemically richer, more diverse, more capable of forming rocky planets and complex molecules. The Webb telescope can measure this chemical enrichment by analyzing the light from early galaxies. Different elements absorb and emit light at characteristic wavelengths. By studying the spectrum of a galaxy's light, scientists can determine which elements are present and in what proportions. Early results suggest that chemical enrichment happened surprisingly quickly in some parts of the early universe. Some galaxies from just a few 100 million years after the Big Bang already contain significant amounts of heavy elements, more than expected given the short time available. This is another piece of the puzzle, another constraint on models of how the first stars formed and evolved. If heavy elements built up quickly, it suggests that star formation in the early universe was intense and efficient. Many massive stars must have formed, lived brief lives, and exploded, releasing their freshly minted atoms into the surrounding gas. The universe was a cauldron of creation, cooking up the elements that would eventually become planets, oceans, and living things. There is poetry in this. The calcium in your bones was forged in the core of a star that exploded before our sun was born. The oxygen you are breathing right now traveled through space for billions of years before becoming part of Earth's atmosphere. We are literally made of star stuff, descendants of stellar generations stretching back to the first lights in the cosmic darkness. The Webb telescope also looks for some of the most energetic events in the universe, gamma-ray bursts. These are brief, intense flashes of high-energy radiation that occur when massive stars collapse or when neutron stars collide. For a few seconds, a gamma-ray burst can outshine entire galaxies. gamma-ray bursts were discovered by accident in the 1960s by military satellites designed to detect nuclear explosions. Scientists quickly realized these flashes were coming from deep space, from unimaginable distances. They remain among the most powerful explosions in the universe, releasing more energy in seconds than our Sun will emit in its entire lifetime. The Webb telescope cannot directly detect gamma rays. Those high-energy photons require specialized detectors, but it can observe the afterglows of gamma-ray bursts, the fading light that lingers after the initial flash. By studying these afterglows, scientists can learn about the environments where gamma-ray bursts occur and the physics of these extreme events. Some gamma-ray bursts occur in the early universe, when the first generations of massive stars were dying. Observing these ancient explosions can tell us about star formation in the cosmic dawn, about the masses and properties of the first stars. It is another window into that distant, formative era. And speaking of windows, let us consider how the telescope actually detects light. At the heart of the Webb telescope are 4 scientific instruments, each designed to capture and analyze infrared light in different ways. One instrument is a camera that takes pictures across a range of infrared wavelengths. These are the stunning images you may have seen: the deep fields full of galaxies, the glowing nebulae, the planetary images. The camera has sensors cooled to extremely low temperatures, allowing them to detect faint infrared photons without being overwhelmed by their own thermal glow. Another instrument is a spectrograph, a device that spreads light out into its component wavelengths, like a prism spreading white light into a rainbow. By examining this spectrum, scientists can identify chemical elements, measure temperatures, and determine how fast objects are moving. Spectrographs are essential for studying the composition and dynamics of cosmic objects. A third instrument is designed specifically to study objects at the longest infrared wavelengths, the light that has been stretched the most by cosmic expansion. This instrument can see the oldest and most distant objects, peering deep into the cosmic dark ages. The fourth instrument is specialized for studying exoplanets. It can block out the light from a star, allowing the much fainter light from nearby planets to be detected. This is called coronagraphy, and it is crucial for directly imaging worlds beyond our solar system. Together, these instruments give the Webb telescope a comprehensive toolkit for exploring the infrared universe. They can image, analyze, measure, and probe a vast range of cosmic phenomena, from nearby asteroids to the most distant galaxies. The data from these instruments flows back to Earth, where teams of scientists download it, process it, and analyze it. The raw data is not immediately beautiful. It must be cleaned and calibrated, corrected for instrumental effects, assembled into usable images and spectra. This processing takes expertise and care. A mistake in data reduction can lead to spurious results. Once the data is ready, scientists begin the detective work. They compare observations to theoretical models. They look for patterns and anomalies. They debate interpretations with colleagues. Eventually, they publish their findings in scientific journals, where other scientists can examine and critique their work. This peer review process is essential to science. It is how the community filters out errors and biases, how it builds a shared understanding based on evidence. No single scientist, no matter how brilliant, has a monopoly on truth. Progress comes from the collective effort of many minds, checking and challenging each other, slowly converging on accurate descriptions of nature. The impossible galaxies are currently in the thick of this process. Different groups of scientists are analyzing the data in different ways, reaching different conclusions. Some are more confident that the observations represent a genuine crisis for standard cosmology. Others are more cautious, pointing out potential sources of error or alternative interpretations. Over time, as more data accumulates and more analyses are performed, the picture will become clearer. This is how science should work. It is messy and contentious, but it is also self-correcting. The truth, whatever it turns out to be, will eventually emerge. Now let us consider one more aspect of the early universe that the telescope has illuminated, the process of reionization. After the Big Bang, the universe was a hot plasma, a soup of ions and electrons. As it cooled, the ions and electrons combined to form neutral hydrogen atoms. This process, called recombination, happened about 380,000 years after the Big Bang. The resulting neutral gas was transparent to light, which is why we can see the cosmic microwave background from that era. For the next few 100 million years, the universe remained mostly neutral. This was the cosmic dark ages, before the first stars and galaxies formed. Then, as the first stars ignited, something dramatic happened. The intense ultraviolet radiation from these stars began to strip electrons from the surrounding hydrogen atoms, turning them back into ions. This process is called reionization, and it transformed the universe from a vast sea of neutral gas into an ionized plasma shot through with light. Reionization was not instantaneous. It proceeded in patches, as bubbles of ionized gas grew around the first stars and galaxies, eventually merging into a fully ionized universe. The details of this process, when it happened, how quickly it proceeded, which sources provided the ionizing radiation, are still being worked out. The Webb telescope is uniquely suited to study this epoch. It can see the galaxies that produce the ionizing radiation. It can measure their properties and estimate how much ultraviolet light they emitted. It can look for the signatures of neutral hydrogen surrounding these early galaxies, the shadows cast by gas that had not yet been ionized. Early results suggest that the galaxies discovered by Webb may have played a significant role in reionization. Their high star formation rates would have produced copious amounts of ultraviolet radiation, potentially enough to ionize vast volumes of surrounding gas. The universe breakers may have been universe changers too, not just impressively large, but also transformative, reshaping the cosmos around them. Reionization marked the end of the cosmic dark ages and the beginning of the universe we see today. After reionization, light could travel freely across vast distances, allowing galaxies to see each other and interact through gravity and radiation. The structures we observe in the modern universe, the cosmic web of galaxies and clusters, began to take shape during this era. Understanding reionization helps us understand how we got here. It connects the hot early universe to the cool, structured universe of today. It is a critical chapter in the cosmic story, and the Webb telescope is helping us read it with unprecedented clarity. Let us return now to the question of what the impossible galaxies might mean for our theoretical understanding. Science is built on models. A model is a simplified description of reality, a set of equations and assumptions that capture the essential features of a system without including every detail. The Big Bang model is such a model. It describes the large-scale evolution of the universe, from a hot, dense state to the cool, expanding cosmos we see today. Models are useful because they make predictions. If the Big Bang model is correct, we should see certain things when we look at the universe. We should see galaxies receding from us. We should see a cosmic microwave background with specific properties. We should see a certain mix of light elements. All of these predictions have been confirmed, which is why the Big Bang model is widely accepted. But models also have limits. They are approximations, not exact descriptions. They work well within certain ranges and break down outside those ranges. The impossible galaxies may be showing us a range where our current models break down, a regime where the approximations we have been using are no longer valid. This is not a failure of science. It is an opportunity. When models fail, we learn something new. We discover that reality is richer than our previous descriptions. We revise and improve our models to account for the new data. Science advances. One specific aspect of the Big Bang model that may need revision is our understanding of galaxy formation. The standard picture involves dark matter playing a central role. Dark matter, as mentioned earlier, is invisible stuff that exerts gravitational pull but does not interact with light. It makes up most of the matter in the universe, roughly 5 times as much as ordinary atomic matter. In the standard model, dark matter clumped together first, forming vast halos and filaments. Ordinary matter then fell into these dark matter structures, attracted by gravity. As ordinary matter accumulated, it formed stars and galaxies. The dark matter provided the scaffolding. Ordinary matter provided the lights. This picture has been very successful at explaining the large-scale structure of the universe, the distribution of galaxies in space, but it has always had some tension with observations of the smallest scales. Simulations of dark matter structure predict more small satellite galaxies around large galaxies like the Milky Way than we actually observe. They predict that the centers of galaxies should have very dense cores of dark matter, denser than observations suggest. These small-scale problems have been debated for years. Various solutions have been proposed, involving different properties of dark matter or effects of ordinary matter that are not well captured in simulations. The impossible galaxies add a new twist. If galaxies grew much faster in the early universe than our models predict, it suggests that something about our understanding of dark matter, or galaxy formation, or both, needs adjustment. One intriguing possibility is that dark matter has properties we have not yet discovered. The standard assumption is that dark matter is cold, meaning it moves slowly relative to the speed of light. Cold dark matter clumps efficiently, forming the kind of structure we see in the universe. But what if dark matter is warmer than we thought? What if it has some slight ability to interact with itself or with ordinary matter in ways we have not detected? These modifications could change how quickly galaxies form and how large they can grow. Another possibility is that the connection between dark matter and ordinary matter is more complex than we assumed. Perhaps feedback processes, like the explosions of supernovas or the energy from active black holes, affect galaxy formation in ways our models have not captured. Perhaps the first galaxies were more efficient at converting gas into stars because the conditions were different, less polluted by heavy elements that can disrupt star formation. These are not idle speculations. They are testable hypotheses. Future observations with the Webb telescope and other instruments can constrain these possibilities, ruling some out and lending support to others. Science is a conversation between theory and observation, and the impossible galaxies have added new voices to that conversation. Let us take a moment now to appreciate the sheer scale of what we are discussing. The light from these early galaxies has been traveling for over 13 billion years. During that journey, the universe has expanded, stretching space itself. When the light was emitted, those galaxies were much closer than they appear to be now. The expansion of space has carried them far away, even as their light was traveling toward us. Today, those galaxies, assuming they still exist in some form, are tens of billions of light years away. We can never reach them. Even traveling at the speed of light, we could never catch up because the space between us is expanding faster than light can traverse it. They are beyond our cosmic horizon, forever unreachable. But their light, emitted long ago, has reached us. That light is a message from the past, a time capsule containing information about a universe that no longer exists. The galaxies we see are not there anymore, not in the form we observe. Billions of years have passed for them. They have evolved, merged with other galaxies, changed in ways we cannot directly observe. We are archaeologists of the cosmos, studying artifacts from a vanished era. The impossible galaxies are ruins of an ancient epoch, monuments to a time when the universe was young and strange. We piece together their story from fragments of light, inferring what they were like based on what little evidence has survived the long journey to our telescopes. This is humbling. It is also inspiring. Despite our limitations, despite the vastness of space and time, we can still learn. We can still discover. We can still be surprised by the universe. And the surprises keep coming. Every new observation from the Webb telescope reveals something unexpected. The early universe was not the simple, quiet place we once imagined. It was vibrant, dynamic, full of activity. The first galaxies burst onto the scene with a vigor that challenges our understanding. What else awaits discovery? What other surprises lurk in the data waiting to be analyzed? We do not know, and that is the beauty of exploration. The unknown beckons, the mystery deepens, and we, driven by curiosity, keep looking. Let us drift now into some reflection on what all of this means for us, as human beings living on a small planet in a vast universe. The discoveries of the Webb telescope do not change our daily lives in any direct way. They do not help us pay our bills or cure our diseases. They do not solve the practical problems we face each day. In a strictly utilitarian sense, they are not useful. But human beings are not strictly utilitarian creatures. We need meaning. We need wonder. We need to feel connected to something larger than ourselves. The cosmos provides that connection. When we look at the stars, we are reminded that we are part of a vast and ancient story, a story that began billions of years before we were born, and will continue billions of years after we are gone. The impossible galaxies are part of that story. They are not just scientific data points. They are windows into our past, glimpses of the universe that made us possible. Without the stars and galaxies that came before, there would be no Earth, no life, no beings capable of building telescopes and wondering about their origins. In studying the cosmos, we are studying ourselves. We are tracing the chain of events that led from the Big Bang to this moment, to you, listening to these words, drifting through the night. Every atom in your body was once part of a star. Every star was once part of a gas cloud. Every gas cloud was once part of the primordial soup that emerged from the Big Bang. You are made of the same stuff as those impossible galaxies, the same elements, the same particles, the same fundamental forces. The universe is not something out there, separate from you. It is something you are part of, intimately and inextricably. You are the universe experiencing itself, contemplating itself, marveling at itself. This perspective can be calming. When the worries of daily life feel overwhelming, it can help to remember the big picture. Your problems are real and important, but they are also small in the grand scheme of things. The universe has been evolving for billions of years. It will continue evolving for billions more. In that vast sweep of time, a bad day or a difficult year is just a tiny moment. This is not meant to diminish your experiences. Your life matters. Your feelings matter. But perspective can bring peace. The universe, for all its violence and chaos, is also a place of profound beauty and order. Stars form and die in cycles that repeat across cosmic time. Galaxies spin in graceful spirals. The laws of physics, elegant and mathematical, govern everything from the smallest particles to the largest structures. There is something reassuring in that order. The universe may be strange, but it is not random. It follows rules, and we, with our curiosity and our tools, can discover those rules. We can make sense of the chaos. We can find meaning in the vastness. The impossible galaxies are a reminder that we do not have all the answers, but they are also a reminder that we can find answers if we keep looking. The universe rewards the curious. It reveals its secrets to those who ask the right questions and make the careful observations. So let us keep asking. Let us keep looking. Let us keep drifting through the cosmos, guided by wonder, sustained by hope. The night is long and full of stars. There is so much more to discover. As we continue our journey through the discoveries of the Webb telescope, let us explore some of the other mysteries it has begun to unravel. One fascinating area of study involves the earliest black holes. Black holes, as you may know, are regions of space where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse at the end of their lives, crushing their cores into points of infinite density. At least, that is how most black holes form. The black holes at the centers of galaxies are much larger, millions or billions of times the mass of our Sun. These supermassive black holes could not have formed from single collapsing stars. They must have grown over time, feeding on gas and merging with other black holes. But growing a supermassive black hole takes time. There are limits to how quickly a black hole can consume matter. As matter falls toward a black hole, it heats up and releases radiation. This radiation pushes back against more matter trying to fall in, creating a kind of traffic jam. The black hole can only eat so fast. Given these limits, astronomers calculated how large black holes could have grown in the early universe. They expected to find relatively small black holes, still in the early stages of growth. Instead, the Webb telescope has found evidence of surprisingly massive black holes existing at very early times. One such object was discovered in a galaxy from about 440 million years after the Big Bang. The black hole at its center has a mass of roughly 10 million solar masses. That is remarkably large for such an early time. It suggests that either black holes can grow faster than we thought, or they started from much larger seeds than we assumed. Several explanations have been proposed. One involves direct collapse black holes. In the standard picture, black holes form from the remnants of dead stars. But in the early universe, under certain conditions, giant clouds of gas might have collapsed directly into black holes without ever forming stars. These direct collapse black holes could have been born big, with masses thousands of times that of the Sun, giving them a head start on growth. Another possibility involves dense star clusters. In the early universe, star clusters may have been much denser than they are today. In these crowded environments, stars could have collided and merged, building up massive stars that then collapsed into massive black holes. These black holes could have grown quickly by consuming nearby gas and merging with each other. A third possibility, more speculative, involves primordial black holes. As mentioned earlier, these hypothetical objects could have formed in the first moments after the Big Bang, from density fluctuations in the hot plasma. If primordial black holes exist, and seeded the centers of early galaxies. They could explain why supermassive black holes appear so early in cosmic history. We do not yet know which explanation is correct. Perhaps all of them play a role. The Webb telescope will continue to observe early black holes, measuring their masses and properties, constraining our theories. In time, we will understand how these cosmic monsters came to be. The study of black holes connects to a broader mystery, the nature of gravity itself. Our best theory of gravity is Einstein's general relativity, published over a century ago. General relativity describes gravity not as a force, but as a curvature of space and time caused by mass and energy. Massive objects bend space around them, and other objects follow the curves of that bent space. General relativity has passed every test we have thrown at it. It predicted the bending of light by the sun, confirmed during a solar eclipse in 1919. It predicted the existence of gravitational waves, ripples in space-time caused by accelerating masses, detected for the first time in 2015. It accurately describes the orbits of planets, the structure of black holes, the expansion of the universe. And yet, we know general relativity is incomplete. It does not mesh well with quantum mechanics, the theory that describes the behavior of particles at the smallest scales. At the center of a black hole, where gravity is strongest and distances are smallest, general relativity predicts a singularity, a point of infinite density, where the laws of physics break down. This singularity is a sign that our theory is missing something, that a deeper theory is needed to describe these extreme conditions. The early universe is another place where general relativity may need modification. At the moment of the Big Bang, the universe was infinitely dense, a singularity in time. What does that really mean? What happened before the Big Bang, if the question even makes sense? General relativity alone cannot answer these questions. We need a theory of quantum gravity, a theory that combines gravity with quantum mechanics, to fully understand the origin and fate of the cosmos. The impossible galaxies, with their challenge to standard cosmology, may be pointing toward the need for new physics. Perhaps general relativity needs modification on cosmic scales. Perhaps dark matter and dark energy, the mysterious components that dominate the universe, behave differently than we assumed. Perhaps there are additional dimensions of space, curled up too small to see, that affect the growth of structure in subtle ways. These are speculative ideas, but they are the kinds of ideas that scientists explore when observations challenge existing theories. The universe is the ultimate laboratory, conducting experiments on scales we could never replicate on Earth. Our job is to watch, measure, and learn. Let us turn now to some of the other instruments that work alongside the Webb telescope, painting a more complete picture of the cosmos. The Webb telescope is not alone in its orbit. It is part of a fleet of space observatories, each designed to see the universe in a different light. The Hubble Space Telescope, mentioned earlier, continues to operate, observing invisible and ultraviolet wavelengths. Together, Hubble and Webb can see the same objects in different kinds of light, revealing different aspects of their nature. On the ground, vast arrays of radio telescopes listen for radio waves from space. The cosmic microwave background, the afterglow of the Big Bang, was discovered using radio telescopes. Radio waves also come from pulsars, quasars, and the gas between stars. Radio astronomy opens a window on phenomena invisible to optical and infrared telescopes. X-ray and gamma-ray telescopes orbit above the atmosphere, detecting high-energy radiation from the most violent events in the universe. Black holes consuming matter, neutron stars spinning and emitting beams of radiation, supernova explosions. All of these produce X-rays and gamma rays. These high-energy observatories complement the Webb telescope's infrared view. Gravitational wave detectors like LIGO and Virgo listen for ripples in spacetime. When massive objects like black holes or neutron stars collide, they shake space itself, sending waves across the cosmos. These gravitational waves carry information about events that produce little or no light, opening an entirely new way of studying the universe. And on the horizon, new instruments are being planned and built. The Vera Rubin Observatory, currently under construction in Chile, will survey the entire visible sky every few nights, cataloguing billions of stars and galaxies, searching for transient events like supernovas and moving objects like asteroids. The giant Magellan Telescope and the extremely large telescope, both under construction, will be ground-based giants with mirrors tens of meters across, capable of seeing fainter and more distant objects than ever before. In space, NASA and other agencies are developing concepts for next-generation observatories. Some would image exoplanets directly, blocking out their parent stars to see the planets clearly. Others would measure the cosmic microwave background with unprecedented precision, searching for signatures of cosmic inflation. Still others would observe the universe in wavelengths that current telescopes cannot access. The future of astronomy is bright. Each new telescope builds on the discoveries of its predecessors. Each new wavelength reveals something that was hidden before. The universe has an infinite capacity to surprise us, and our tools for exploration keep improving. Let us now consider the philosophy of science itself, the principles that guide our search for understanding. Science is often described as a method. You observe the world, form a hypothesis, make predictions, test those predictions with experiments or observations, and revise your hypothesis based on the results. This method, refined over centuries, is remarkably effective at uncovering truths about nature. But science is also a culture, a set of values and practices shared by a community. Scientists are expected, to be honest, to report their results accurately even when those results are unexpected or unwelcome. They are expected to share their methods so others can check their work. They are expected to consider alternative explanations and acknowledge uncertainties. These cultural norms are what make science self-correcting. No individual scientist is infallible. We all have biases and blind spots. But the collective enterprise of science, with its peer review and replication and open debate, gradually filters out errors and converges on truth. The impossible galaxies illustrate this process in action. The initial observations were surprising. Some scientists were excited, seeing them as evidence for new physics. Others were cautious, worrying about potential errors in the measurements. Both responses are valuable. The excited scientists push us to consider new possibilities. The cautious scientists ensure we do not abandon good theories based on flimsy evidence. Over time, more observations will be made. The distances and masses of these early galaxies will be measured with greater precision. Alternative explanations will be tested and either supported or ruled out. Eventually, the scientific community will reach a consensus on what the impossible galaxies mean. This process is slow. It can be frustrating to those who want quick answers. But the slowness is the price of reliability. By insisting on rigorous evidence and open debate, science produces knowledge we can trust. The conclusions it reaches, while always provisional, are the best descriptions of reality we have. Philosophy can also help us appreciate what science does and does not tell us. Science describes how the universe works. It tells us that galaxies form from gas collapsing under gravity, that stars shine by nuclear fusion, that light travels at a finite speed. These are facts about the mechanisms of nature. But science does not tell us why the universe exists, or whether it has a purpose, or what makes a good life. These are questions for philosophy, religion, and personal reflection. Science is one way of knowing, perhaps the most reliable way for understanding the physical world, but it is not the only way of knowing. A complete human life involves many ways of engaging with the world, including art, love, ethics, and spirituality. The discoveries of the Webb telescope can enrich all of these dimensions of life. The beauty of a nebula can inspire an artist. The vastness of the cosmos can deepen a sense of spiritual awe. The story of our cosmic origins can inform ethical reflections on our place in nature. Science and the humanities are not rivals. They are partners in the human quest for understanding and meaning. Let us drift now into some of the more detailed observations the telescope has made about specific objects. One intriguing target is a galaxy called GN-Z11. Before the Webb telescope launched, GN-Z11 was the most distant galaxy known, observed by the Hubble Space Telescope at a redshift, indicating it existed about 400 million years after the Big Bang. The Webb telescope has now studied this galaxy in greater detail, revealing its properties with unprecedented clarity. GN-Z11 is remarkably bright for such an early galaxy. It is forming stars at a high rate, several dozen solar masses per year. It is also compact, smaller than the Milky Way, but surprisingly luminous. Some observations suggest it may host an active black hole at its center, which could contribute to its brightness. The detailed study of GN-Z11 helps astronomers understand what early galaxies were like. Each observation adds a data point, a piece of the puzzle. As more early galaxies are studied in detail, patterns will emerge, common properties that reveal how galaxies formed and evolved in the cosmic dawn. Another fascinating target is a galaxy called SPT 615JD. This galaxy is so distant that its light has been stretched by the expansion of space to infrared wavelengths. But it has another remarkable feature. It is gravitationally lensed by a massive galaxy cluster that lies between it and us. Gravitational lensing occurs when the gravity of a massive object bends the light from a more distant object. The massive object acts like a lens, magnifying and distorting the image of the background object. In some cases, the lensing creates multiple images of the same background object stretched and curved around the foreground lens. SP0615JD is magnified by gravitational lensing by a factor of several hundred. This magnification allows the Webb telescope to see details that would otherwise be too faint to detect. The galaxy appears as a thin arc of light, stretched by the lensing effect. Scientists can study its structure and composition with a level of detail impossible for unlensed objects at similar distances. Gravitational lensing is a powerful tool for studying the early universe. It effectively turns galaxy clusters into cosmic telescopes, boosting the power of our instruments. The Webb telescope is using lensing to observe some of the most distant objects ever detected, probing deeper into cosmic history than would otherwise be possible. There is something elegant about using gravity itself to enhance our vision. Einstein predicted gravitational lensing over a century ago, based on his theory of general relativity. Now we use it routinely, exploiting the warping of space to see farther and clearer. The universe provides the tools for its own exploration. Let us consider now the role of computer simulations in modern astronomy. Observing the universe is only half the battle. To understand what we see, We need theories and models. These models are often expressed mathematically as equations that describe how matter and energy behave. But for complex systems like galaxies, analytical equations are not enough. The systems are too complicated, with too many interacting parts. We need computers to simulate them. Cosmological simulations start with initial conditions based on the cosmic microwave background, tiny fluctuations in density in the early universe. They then follow the evolution of matter over billions of years, tracking how gravity pulls gas into filaments and halos, how stars form and die, how black holes grow and feedback on their surroundings. These simulations run on the world's largest supercomputers, performing trillions of calculations. The results are virtual universes, digital replicas that can be compared to observations. If the simulations match reality, we gain confidence that our understanding is correct. If they do not match, we know something needs to be fixed. The impossible galaxies pose a challenge for simulations. Standard simulations using our best current understanding do not produce such large galaxies so early in cosmic history. The simulations fall short, predicting smaller, dimmer galaxies than what the Webb telescope observes. This discrepancy is a signal that something in our models needs adjustment. Scientists are now tweaking their simulations, testing different assumptions about star formation, black hole growth, dark matter properties, and more. Some modifications bring the simulations closer to the observations. Others do not help. Through this process of trial and error, we will eventually find the right ingredients to reproduce the observed universe. Simulations are not just tools for testing theories. They also generate predictions. A good simulation tells us what we should see when we point our telescopes at a particular part of the sky. It predicts the number of galaxies, their sizes, their colors, their distributions. These predictions can be tested with future observations, further refining our models. The interplay between observation and simulation is central to modern astrophysics. Neither alone is sufficient. Observations without models are just data, points of light with no context. Models without observations are just speculation, untethered from reality. Together, they form a powerful cycle of discovery. Let us also acknowledge the role of serendipity in science. Some of the greatest discoveries happen by accident, when scientists find something they were not looking for. The cosmic microwave background was discovered by accident in 1964. Two radio engineers, Arno Penzias and Robert Wilson, were trying to calibrate a sensitive antenna at Bell Labs in New Jersey. They kept detecting a faint hiss of static that they could not explain or eliminate. After ruling out every possible source of interference, including pigeons nesting in the antenna, they realized the hiss was coming from space. It was the afterglow of the Big Bang, the oldest light in the universe. Pulsars were discovered by accident in 1967. A graduate student named Jocelyn Bell was analyzing data from a radio telescope, looking for quasars. She noticed a strange, repeating signal, a blip that appeared at regular intervals. At first, it was jokingly called LGM1 for little green men, because the regularity suggested an artificial source. But it turned out to be a pulsar, a rapidly spinning neutron star emitting beams of radio waves like a lighthouse. The accelerating expansion of the universe was discovered by accident in 1998. Two teams of astronomers were using distant supernovas to measure the rate of cosmic expansion. They expected to find that the expansion was slowing down due to the gravitational pull of matter. Instead, they found it was speeding up, driven by the mysterious force we call dark energy. The Webb telescope may have its own accidental discoveries. In searching for one thing, it may stumble upon something entirely unexpected. The data archives are vast, and not all anomalies are immediately noticed. Future scientists, analyzing old data with new tools and new questions, may find surprises we cannot anticipate. This is the adventure of science. We set out with plans and expectations, but the universe has the final say. It shows us what it wants to show us, when it wants to show us. Our job is to pay attention and remain open to surprise. As we near the end of our journey through the discoveries of the Webb telescope, let us consider what remains to be done. The telescope has been operating for only a few years. It has a planned lifetime of at least 10 years, perhaps longer if everything continues to work well. In that time, it will make countless more observations, revealing new details about the early universe, exoplanet atmospheres, star-forming regions, and much more. Some of these observations are already planned. Scientists have submitted proposals requesting telescope time for specific projects. Committees have reviewed these proposals and allocated time to the most promising ones. The telescope's schedule is mapped out months in advance, a carefully choreographed dance of observations and calibrations. Other discoveries will come from data that has already been collected, but not yet fully analyzed. The archives of the Webb telescope are growing every day, filled with images and spectra waiting to be studied. Scientists around the world are downloading this data, applying their expertise, searching for patterns and anomalies. The impossible galaxies were found this way, by scientists poring over the first deep field images, looking for the most distant objects. Still other discoveries will come from follow-up observations of interesting targets. When something unusual is found, more telescope time can be requested to study it in greater detail. The impossible galaxies, for example, will be observed again and again with different instruments and at different times to confirm and refine the initial findings. And beyond the Webb telescope, other instruments will continue the exploration. Ground-based telescopes, future space telescopes, gravitational wave detectors, all will contribute to our understanding. The cosmic puzzle has many pieces, and different instruments see different parts. The goal, ultimately, is a complete and coherent picture of the universe. We want to understand how it began, how it evolved, how galaxies and stars and planets formed, how life emerged. We want to place ourselves in context, to know our origins and our place in the cosmic story. We are not there yet. The impossible galaxies remind us how much we do not know. But we are making progress. Each generation of scientists stands on the shoulders of those who came before, seeing a little further, understanding a little more. The journey is long, but the direction is clear. As the telescope continues its vigil in the cold darkness of space, let us take a moment to appreciate the human story behind this machine. The James Webb Space Telescope was named after James Webb, who served as the second administrator of NASA from 1961 to 1968. During his tenure, NASA laid the groundwork for the Apollo program, which would eventually land humans on the moon. Webb believed in the importance of science, not just exploration for its own sake, but the systematic study of the universe. It is fitting that a telescope of such scientific ambition bears his name. But the telescope is really the work of thousands of people, most of whose names will never be widely known. Engineers who designed the intricate mechanisms that allowed the telescope to unfold in space. Technicians who assembled the mirrors with painstaking precision. Scientists who spent years developing the instruments and planning the observations. Managers who navigated budgets and schedules and bureaucracy. astronauts who serviced the Hubble Space Telescope in orbit, demonstrating that complex space repairs are possible, teachers who inspired the next generation of explorers. All of these people contributed to the telescope, even if their names do not appear on the official record. This is true of all great scientific endeavors. They are collective achievements, products of communities rather than individuals. The lone genius, working in isolation to achieve breakthroughs, is largely a myth. Real science happens through collaboration, through the sharing of ideas and data and criticism. The Webb telescope is a monument to this collective human spirit. Consider the international nature of the project. The telescope was built by NASA in partnership with the European Space Agency and the Canadian Space Agency. Components were manufactured in countries around the world. Scientists from many nations contributed to its design and will use it for observations. In a world often divided by borders and politics, the telescope represents a kind of unity, a shared commitment to understanding our place in the cosmos. This international cooperation is practical as well as symbolic. Space missions are expensive and complex. No single country, no matter how wealthy or advanced, can do everything alone. By pooling resources and expertise, nations can accomplish more together than they could separately. The International Space Station is another example of this principle, a habitat orbiting Earth built and operated by multiple countries working in partnership. Perhaps one day this cooperation will extend beyond Earth. Perhaps humans will establish outposts on the Moon, on Mars, on moons of Jupiter and Saturn. Perhaps we will send probes to other star systems, building on the discoveries of telescopes like Webb to choose the most promising destinations. These future explorations will require even greater cooperation, bringing together not just nations, but perhaps generations. For now, we explore with light. We send out our machines to listen and watch, gathering photons from across the universe, assembling them into images and spectra, reading the stories they tell. It is a kind of cosmic conversation, a dialogue between distant objects and curious observers, mediated by the speed of light. The light from the impossible galaxies has been traveling since long before Earth existed. When that light began its journey, our sun had not yet formed. The solar system was not even a gleam in the eye of some ancient supernova. Dinosaurs, humans, cities, telescopes, all of these lay billions of years in the future. The light traveled through an expanding, evolving universe, crossing unimaginable distances, finally arriving at a detector built by beings who did not exist when it departed. There is something miraculous about this. Light carries information across time and space, connecting events separated by billions of years. The photons detected by the Webb telescope are messengers from the ancient past, ambassadors from an epoch we can visit only with our instruments. They bring news of a universe that no longer exists, a cosmos transformed beyond recognition by the passage of time. This is time travel, in a sense, not the dramatic kind imagined in science fiction, where travelers step through portals into different eras, but a gentler kind, where information from the past flows into the present, allowing us to witness events that happened long ago. Every time we look at the stars, we are looking backward in time. The Webb telescope simply extends this reach to its limits, but there are limits. Beyond a certain distance, beyond a certain age, we cannot see. The cosmic microwave background marks a kind of wall in time, beyond which the universe was opaque. Before recombination, photons could not travel freely. They scattered off electrons, bouncing randomly through the hot plasma. There is no light from that era that we can detect. The cosmic microwave background is our earliest snapshot, and what lies beyond is hidden. Some physicists speculate about ways to probe even earlier epochs. Gravitational waves, for example, could in principle carry information from times before the cosmic microwave background was emitted. The early universe should have produced primordial gravitational waves. Ripples in space-time stretched to cosmic scales by the expansion that followed. These waves might leave subtle imprints on the cosmic microwave background or on the distribution of galaxies. Detecting and interpreting these imprints is a major goal of observational cosmology. Neutrinos offer another possibility. These ghostly particles interact very weakly with matter, passing through planets and stars with ease. In the early universe, neutrinos decoupled from the rest of matter even before photons did. They have been streaming freely through space ever since, carrying information from an earlier epoch. The cosmic neutrino background, as it is called, is much fainter than the cosmic microwave background and has not yet been directly detected. But future experiments might succeed, opening yet another window on the past. And then there are theoretical possibilities, ideas that push beyond established physics into the realm of speculation. Perhaps the universe cycles through phases, expanding and contracting in eternal succession. Perhaps our Big Bang was not the beginning, but a transition from a previous era. Perhaps information from before the Big Bang could survive, encoded in subtle features of the cosmos we observe today. These ideas are highly speculative. We have no evidence for them, but they illustrate the depth of the questions that cosmology grapples with. Where did the universe come from? Why does it exist? What, if anything, came before? These are the ultimate questions, the ones that keep physicists and philosophers awake at night. The Webb telescope will not answer these deepest questions. It is designed to observe the universe as it is and was, not to explain why it exists. But by showing us more clearly what the universe looks like, it constrains our theories and inspires new ideas. The impossible galaxies are a case in point. They force us to rethink our models, to consider possibilities we had not taken seriously. In doing so, they advance our understanding, even if they do not provide ultimate answers. Let us consider now the future of cosmology, the next steps in our quest to understand the universe. One major goal is to understand dark energy, the mysterious force accelerating the expansion of the cosmos. Dark energy makes up about 68% of the total energy content of the universe. We know it exists because of its effects on the expansion rate, but we do not know what it is. The simplest possibility is that dark energy is a cosmological constant, a constant energy density inherent to empty space. Einstein introduced this term into his equations of general relativity, then later called it his greatest blunder when the universe was found to be expanding. But the discovery of accelerating expansion revived the cosmological constant. If dark energy is indeed constant, it would remain fixed forever, and the universe would continue expanding at an ever-increasing rate. Other possibilities exist. Dark energy might vary over time, growing stronger or weaker as the universe evolves. It might interact with dark matter in unexpected ways. It might be the signature of modifications to gravity on cosmic scales. Distinguishing between these possibilities requires precise measurements of the expansion history and the growth of cosmic structure. Several experiments are underway or planned to study dark energy. The Dark Energy Spectroscopic Instrument is mapping the three-dimensional positions of millions of galaxies, tracing the cosmic web over billions of years of cosmic history. The Euclid space mission, launched by the European Space Agency, will survey large swaths of sky, measuring the shapes of distant galaxies distorted by gravitational lensing. The Nancy Grace Roman Space Telescope, scheduled to launch in the coming years, will combine imaging and spectroscopy to study dark energy and much more. Together, these experiments will provide a detailed picture of how the universe has expanded and how structure has grown. They will test our theories of dark energy and gravity, potentially revealing surprises as dramatic as the impossible galaxies. Another major goal is to detect and study primordial gravitational waves. As mentioned earlier, inflation, the hypothesized period of rapid expansion in the first fraction of a second, should have generated gravitational waves. These waves have been stretched by the subsequent expansion to wavelengths spanning the observable universe. They could leave a distinctive imprint on the cosmic microwave background, a pattern called B-mode polarization. Several experiments are searching for this B-mode signature. They use sensitive detectors to measure the polarization of the cosmic microwave background with exquisite precision. So far, no primordial signal has been definitively detected, but the sensitivity of the experiments is improving, and a detection could come in the coming years or decades. Finding primordial gravitational waves would be transformative. It would provide direct evidence for inflation, confirming a theory that has been influential but never conclusively proven. It would give us information about the universe at energies far beyond what particle accelerators can achieve. It would open a window on the very earliest moments after the Big Bang, a time we can otherwise only speculate about. Yet another goal is to understand the nature of dark matter. Despite decades of searching, we have not detected dark matter particles directly. We know dark matter exists from its gravitational effects, but its fundamental nature remains unknown. The leading hypothesis is that dark matter consists of weakly interacting massive particles, or WIMPs. These hypothetical particles would have just the right properties to explain the observed abundance of dark matter. They would interact through gravity and possibly through the weak nuclear force, but not through electromagnetism, which is why they are invisible. Experiments around the world are searching for WIMPs. Deep underground detectors wait for rare collisions between dark matter, particles and ordinary atoms. Particle colliders try to produce dark matter particles in high-energy collisions. Space-based instruments look for gamma rays and other signals from dark matter annihilation in the cosmos. So far, these searches have come up empty. This null result is itself informative. It rules out many models of dark matter, narrowing the possibilities. But it also raises questions. If dark matter is not made of WIMPs, what is it? Could it be something entirely different? Something we have not yet imagined? Alternative candidates include axions, very light particles originally proposed to solve a problem in the physics of the strong nuclear force. Axion dark matter would behave differently from WIMPs, forming fuzzy clouds rather than concentrated halos. Experiments are being built to search for axion dark matter, using sensitive magnetometers and resonant cavities. Another possibility is that dark matter is primordial black holes, as discussed earlier. If a significant fraction of dark matter consists of small black holes formed in the early universe, it would explain the gravitational effects we observe without requiring new particles. Observations constrain the allowed masses and abundances of primordial black holes, but a window remains open for them to contribute to dark matter. The nature of dark matter is one of the great unsolved problems in physics. Whoever solves it will earn a place in the history of science alongside Newton and Einstein. The Webb telescope contributes indirectly by studying the effects of dark matter on galaxy formation and evolution. But a direct detection, if it comes, will likely come from dedicated dark matter experiments on Earth or in space. As we contemplate these future goals, let us also consider the deeper questions that drive cosmological research. Why is the universe the way it is? Why does it have the particular laws and constants that it does? Why are the fundamental forces the strengths they are? Why does matter exist at all? These questions venture beyond physics into philosophy. Some scientists argue that such questions are meaningless, that the universe simply is what it is and needs no further explanation. Others argue that we should search for deeper principles, underlying reasons that explain why the universe has its observed properties. One influential idea is the anthropic principle. This principle notes that we can only observe a universe that is compatible with our existence. If the laws of physics were different, if the constants had other values, life as we know it might not be possible. We could not observe such universes because we would not exist in them. This selection effect might explain why the universe seems fine-tuned for life. The anthropic principle comes in various forms, some more controversial than others. In its weak form, it is simply a reminder that our observations are constrained by our existence. In its strong form, it suggests that the universe must have the properties necessary for observers to arise. Critics argue that the strong form is untestable and unscientific. Supporters argue that it might be the best explanation we can hope for, given the limitations of human knowledge. Related to the anthropic principle is the multiverse hypothesis. This idea suggests that our universe is one of many, perhaps infinitely many, each with different properties. Most universes in this multiverse would be barren, with laws and constants that do not permit stars, planets, or life. Only a tiny fraction would be hospitable to observers. We find ourselves in one of these rare habitable universes because we could not exist in any other. The multiverse is a controversial idea. It might be untestable, at least with current technology. If other universes exist, but are completely disconnected from ours, we might never obtain direct evidence for them. But the multiverse is not pure speculation. It arises naturally from certain theories of physics, including inflationary cosmology and string theory. If these theories are correct, the multiverse might be a necessary consequence. These deep questions connect to even deeper ones. Why is there something rather than nothing? Why does existence exist? Philosophy and religion have grappled with these questions for millennia. Science, with its focus on observable, testable phenomena, may never provide complete answers, but it can illuminate the questions, showing how far reason and observation can take us before they reach their limits. The Webb Telescope, in revealing the impossible galaxies and the wonders of the early universe, adds to this illumination. It shows us that reality is stranger than we imagined, that our understanding is incomplete, that more mysteries await. This is not a reason for despair, but for excitement. The adventure of discovery continues. As our journey through the discoveries of the Webb Telescope draws toward a close, let us return to the feelings of wonder and peace that the cosmos can inspire. The universe is vast beyond comprehension. It contains billions of galaxies, each with billions of stars, spread across billions of light years. In this immensity, we are tiny, specks of dust on a mote of rock, orbiting an ordinary star. Our lives are brief, flickers of consciousness in an ocean of time. And yet, we matter. We are the universe becoming aware of itself. Through our eyes, the cosmos sees its own grandeur. Through our minds, it contemplates its own mysteries. We are not separate from the universe. We are part of it, woven into its fabric, participants in its unfolding story. The impossible galaxies, those ancient structures that defy our expectations, are part of our heritage. They are the distant ancestors of the Milky Way, the cosmic generations that came before. Their light, traveling for billions of years, carries information about our origins. By studying them, we learn about ourselves. This connection spans not just space but time. The atoms in your body were forged in stars that died before the Earth was born. The elements that make up your cells pass through multiple stellar generations, scattered by supernovas, gathered into clouds, incorporated into planets, and eventually into living things. You are made of ancient matter, matter that has been part of the universe since its earliest days. The light from the impossible galaxies is even older. It comes from an era when that ancient matter was just beginning to organize itself, when gravity was pulling gas into the first stars and galaxies. The light carries a memory of that formative time, a record preserved across the eons. When you look at the night sky, you are looking at your own history. The stars are your cousins, born from the same cosmic processes that created you. The galaxies are your extended family, members of the same universal community. The universe is your home, the only home any of us will ever know. This perspective can bring peace. The worries and struggles of daily life, while real and important, are small compared to the vastness of the cosmos. Whatever difficulties you face, the stars will still shine. The galaxies will still spin. The universe will continue its majestic evolution, indifferent to our troubles, but also indifferent to our fears. There is comfort in that indifference. It means that the universe does not judge you. It does not demand that you succeed or punish you for failing. It simply is a vast and beautiful backdrop against which the drama of life plays out. You are free to find your own meaning, to create your own purpose within this cosmic context. The Webb Telescope, with its impossible galaxies and stunning images, invites us to find that meaning. It shows us that the universe is full of wonders, waiting to be discovered. It reminds us that curiosity is a powerful force, capable of reaching across billions of years to touch the earliest moments of cosmic time. It suggests that the adventure of understanding is never finished, that there will always be more to learn, more to explore, more to wonder at. And so we return to where we began, to the golden eye floating in the darkness, watching the cosmos with patience and precision. The James Webb Space Telescope has looked too deep into space. It has seen things that challenge our understanding, galaxies that should not exist, structures that form too quickly, light from an era we thought we knew but clearly do not. It has shown us that the universe is stranger than we imagined, richer than our theories, more full of surprises. But it has also shown us something else. It has shown us that we are capable of building machines that can see across billions of years. We are capable of asking questions that span cosmic time. We are capable of being surprised, of admitting our ignorance, of revising our ideas in the face of new evidence. This capacity for wonder and humility is as remarkable as any galaxy, as worthy of celebration as any scientific discovery. The impossible galaxies are not problems to be solved and forgotten. They are invitations. They invite us to think more deeply, to imagine more boldly, to question more carefully. They remind us that science is not a collection of fixed truths, but a living, evolving process of discovery. What we know today will be superseded by what we learn tomorrow. And that is not a flaw but a feature. Science grows by being wrong, by finding its mistakes and correcting them. We do not yet know what the impossible galaxies will teach us. Perhaps they will lead to revisions in our understanding of dark matter. Perhaps they will reveal new physics in the early universe. Perhaps they will turn out to be less impossible than they first appeared, explained by processes we had overlooked. Whatever the answer, the journey to find it will be worthwhile. Let us reflect now on the nature of knowledge itself. Human beings have always sought to understand the world around them. We look for patterns, for regularities, for causes and effects. We build mental models of reality and test them against experience. When our models fail, we revise them or replace them. This process of modeling and testing is the foundation of all knowledge, from the simplest everyday understanding to the most sophisticated scientific theories. The universe, in its vastness and complexity, challenges our models at every turn. It presents phenomena we have never encountered, scales we cannot directly experience, processes that operate over time spans longer than human existence. Our models are approximations, simplifications of a reality far more intricate than any human mind can fully grasp. And yet, our models work. Newton's laws of motion, developed over 3 centuries ago, still accurately describe how objects move. Maxwell's equations of electromagnetism, formulated in the 19th century, underpin all modern technology. Einstein's theories of relativity, now over a century old, continue to pass every test we devise. These models are not perfect descriptions of reality, but they capture something essential, some deep structure that allows us to predict and explain. The impossible galaxies reveal the limits of our current models. They show us where our approximations break down, where the true complexity of the universe exceeds our simplified descriptions. This is valuable information. It tells us where to look for new physics, where to invest our efforts in theoretical development. At the same time, the success of our models in so many other contexts is remarkable. The same physics that describes particles in accelerators describes stars in galaxies. The same gravity that holds you to Earth holds galaxies in clusters. The universe operates by consistent rules, and we can discover those rules through careful observation and reasoning. This consistency is not guaranteed. There is no logical reason why the universe should be understandable by human minds. We are, after all, products of evolution, shaped by natural selection, to survive and reproduce on a particular planet, not to comprehend the cosmos. And yet, somehow, our minds are capable of grasping cosmic truths. We can use mathematics, a creation of human thought, to describe the behavior of galaxies billions of light years away. This is an astonishing fact, a deep mystery that underlies all of science. Some philosophers call this the unreasonable effectiveness of mathematics. Mathematics seems to have a connection to physical reality that goes beyond mere coincidence. The patterns we discover in abstract thought mirror the patterns we find in nature. Why this should be so, no one fully knows. But it is a gift, a bridge between mind and cosmos that allows us to participate in the universe's self-understanding. The Webb telescope is a tool of that understanding. It extends our senses, allowing us to perceive what unaided eyes could never see. It converts the faint infrared glow of distant galaxies into data that our minds can process. It bridges the gap between human scale and cosmic scale, making the vast and ancient accessible to the small and brief. And in doing so, it enriches our lives. Science is not just a collection of facts. It is a source of meaning, a way of connecting to something larger than ourselves. The discoveries of the Webb telescope add to the tapestry of human knowledge, threads that will be woven into the fabric of future understanding. We are part of something ongoing, a project of discovery that began with our earliest ancestors and will continue long after we are gone. Let us drift now toward the end of our journey, toward a place of peace and reflection. The universe is old. 13.8 billion years have passed since the Big Bang, and in that time, countless stars have been born and have died. Galaxies have formed, collided, merged, and evolved. The cosmos has grown larger and colder, its light spreading thinner across an ever-expanding expanse. And yet, the universe is also young. Compared to its potential lifetime, the current age is just the beginning. Stars will continue to form for trillions of years, as long as there is hydrogen to fuel them. Galaxies will continue to evolve, their populations changing as generations of stars live and die. The universe is in its infancy, with most of its history still ahead. We are privileged to exist at this particular moment. We live in an era when the universe is still active, still creating, still changing. The stars that light our nights are not eternal. They will burn out eventually, leaving the cosmos dark and cold. But that final darkness lies unimaginably far in the future, so far that human minds can scarcely conceive it. For now, the stars shine, the galaxies spin, the cosmic drama unfolds, and we, tiny observers on a small planet, have the chance to witness it, to participate in it, to add our own small chapter to the story. The impossible galaxies are part of that story. They are ancestors we did not know we had, relatives from the distant past who turn out to be more accomplished than we expected. They challenge our assumptions and expand our horizons. They remind us that the universe is full of surprises, that our understanding is always incomplete, that there is always more to learn. As the night deepens and the stars wheel overhead, let us carry this sense of wonder with us. Let us remember that we are made of star stuff, that our atoms were forged in cosmic furnaces, that we are connected to the universe in the most intimate possible way. Let us be humble before the vastness of what we do not know, and grateful for the opportunity to know anything at all. The Webb telescope continues its watch, gathering light from the edge of time. Each photon it collects is a message from the past, a note in a bottle thrown across the cosmic ocean, finally reaching shore. We read these messages as best we can, piecing together the story they tell, adding their wisdom to our own. And when we have done all we can, when we have pushed our understanding as far as it will go, we must accept that some things will remain beyond our reach. The ultimate questions may never be answered. The deepest mysteries may never be solved, but the pursuit itself is worthwhile. The journey is its own reward. As you drift into sleep, let the universe hold you. Let the vast distances comfort rather than frighten. Let the ancient light soothe rather than disturb. You are part of something immense and beautiful, something that has been unfolding for billions of years and will continue for billions more. You belong to the cosmos, and the cosmos, in some sense, belongs to you. The stars are watching. The galaxies are spinning. The light is traveling across the void, carrying its ancient cargo of information and beauty. Somewhere out there, the impossible galaxies continue their existence, changed, beyond recognition from the images we have captured, but still there, still real, still part of the cosmic family. Rest now. Let the mysteries settle around you like a blanket. Let the questions drift, unanswered but present, companions on your journey into sleep. Tomorrow the sun will rise, as it has for billions of years, powered by the same nuclear fires that burn in distant suns. The world will continue, with all its joys and sorrows, all its challenges and wonders. But tonight, let the universe be your guide. Let it lead you through the darkness, past the impossible galaxies, into the quiet places where thought gives way to dream. The cosmos is patient. It will wait for you to wake. It will be there when you return, full of new discoveries, new mysteries, new invitations to wonder. The golden eye of the telescope watches still, patient and precise, gathering light from the dawn of time. It sees what we cannot see, hears what we cannot hear, touches the edge of the knowable, and in doing so, it reminds us who we are. We are the children of stars. We are the inheritors of cosmic history. We are the universe looking back at itself, marveling at its own existence, drifting gently into the night. The light has traveled so far to reach us. Let us honor that journey by being present to receive it, by opening our minds and hearts to the messages it carries. Let us be worthy of the universe that made us, curious and humble and full of wonder. And now, as the night grows late and the stars shine on, let yourself drift. Let the vastness of space cradle you. Let the depth of time support you. The cosmos is your home. You are safe here, held by gravity and light, connected to everything that ever was or ever will be. The impossible galaxies shine in the darkness, impossibly bright, impossibly old, impossibly beautiful. They are waiting for us to understand them. They are patient, as the universe is patient, as time itself is patient. One day, perhaps, we will know their secrets. But even if we never do, we will have tried. We will have looked up at the sky and wondered. We will have built our machines and gathered our data and asked our questions. We will have been human in the deepest and best sense of that word. And that is enough. That is more than enough. That is everything. Sleep now. The universe holds you. The stars are singing their ancient songs. The light is flowing across the void, connecting past to present, distant to near, unknown to known. You are part of this flow, this river of light and time. You always have been. You always will be. Rest in that knowledge. Rest in that wonder. Rest in the arms of the cosmos, vast and beautiful and strange, full of impossible things, waiting to be discovered, waiting to be loved. The night is long and deep. The stars are many. The universe is old and young, simple and complex, known and unknown. It is everything and nothing, all at once, all the time. And you are here, in this moment, in this place, breathing this air, feeling this life. You are the universe experiencing itself. You are the cosmos dreaming of itself. You are the light that traveled all this way, finally coming home. Let that be enough. Let that be peace. Let that be the end of the journey and the beginning of the next. Good night, traveler. The stars will keep watch while you sleep. The galaxies will spin their slow spirals. The universe will continue its endless dance. And you, child of stars, dreamer of dreams, will rest in its embrace until morning comes and the light returns and the adventure begins again. Until then, drift, float, dream. The cosmos is with you, always. Before we fully surrender to sleep, let us linger a moment longer on the wonders we have explored. The universe speaks in many voices. It speaks through light, the photons that carry information across the void. It speaks through gravity, the invisible force that shapes the cosmos. It speaks through time, the patient unfolding of cause and effect across billions of years. And it speaks through silence, the vast empty spaces between stars and galaxies where nothing moves and nothing changes. The Webb telescope has taught itself to listen to all these voices. Its golden mirrors catch photons that have been traveling since before Earth existed. Its instruments decode the messages hidden in wavelengths our eyes could never perceive. Its position at the edge of our planetary system gives it access to the quietest corner of the sky, where the voice of the distant universe can be heard above the noise of nearby things. What stories those voices tell! They speak of fires in the dark, the first stars igniting after the cosmic dawn. They speak of collisions and mergers, galaxies crashing together in slow motion dances that span millions of years. They speak of creation and destruction woven together, supernovas that end one generation of stars while seeding the next. They speak of time itself, stretched and warped by the expansion of space, making the past directly visible to those who know how to look. We are learning to read these cosmic messages. Each discovery adds a new word to our vocabulary, a new concept to our understanding. The impossible galaxies have given us new words, words like universe breaker and cosmic crisis. These words point to ideas we are still forming, theories we are still testing. In time, they will either become part of established knowledge or be replaced by better words, more accurate concepts. This is the nature of learning. We start in darkness, not knowing what we do not know. Then we encounter something unexpected, something that does not fit our existing framework. We struggle to understand it, proposing and discarding explanations. Eventually, if we are fortunate, we find a way to accommodate the new observation, expanding our framework to include what was once impossible. What seemed like a crisis becomes an opportunity. What seemed like a problem becomes a breakthrough. The history of astronomy is full of such breakthroughs. Each one seemed impossible at first, a violation of everything known and accepted. The idea that Earth orbits the Sun was once heresy. The idea that the Milky Way is one galaxy among billions was once unthinkable. The idea that the universe began in a hot, dense state and has been expanding ever since was once speculation. Now these are basic facts, taught in elementary schools, accepted by everyone. The impossible, galaxies may follow the same path. What seems impossible today may seem obvious tomorrow. Future generations, looking back at our confusion, may wonder why we found it so difficult to understand. They will have knowledge we do not yet possess, theories we have not yet invented, instruments we have not yet built. They will see further because they will stand on our shoulders, benefiting from our struggles and our failures, as well as our successes. This is the gift we give to the future. Not answers necessarily, but questions. Not certainties, but puzzles worth solving. The Webb Telescope and its impossible galaxies are part of this gift, a legacy of wonder that will inspire generations not yet born. And in the meantime, we have the privilege of being here, at this moment, when the questions are still fresh and the answers are still unknown. We get to experience the excitement of discovery, the thrill of the new. We get to wonder, to speculate, to debate. We get to be confused in the best possible way, confused by a universe more interesting than we expected. So let the confusion comfort you. Let the mystery soothe you. Let the unknown be not a source of fear, but of excitement. The universe is offering you an adventure, an invitation to participate in the grandest exploration ever undertaken. All you have to do is accept. Close your eyes now and imagine the golden telescope, floating in its cold orbit, silently collecting light. Imagine the photons arriving one by one, each carrying a tiny piece of information from the distant past. Imagine the data flowing back to Earth, the scientists poring over their screens, the discovery taking shape. Imagine the impossible galaxies, burning bright in the early universe, building themselves from hydrogen and helium, defying our expectations. Imagine the stars forming within them, the black holes growing at their centers, the chemical elements being forged and scattered. Imagine the light leaving those galaxies, beginning its long journey toward us, traveling through expanding space for billions of years. And imagine yourself, here at the end of that journey, receiving that ancient light, processing that ancient information, becoming part of the chain of understanding that stretches from the cosmic dawn to this present moment. You are connected to those impossible galaxies, linked by the light that spans the ages. This connection is real. It is not metaphor or poetry, but physics. The photons that enter your eyes when you look at the night sky are the same. Photons that left their sources long ago. They have traveled unchanged through the void, carrying their information intact. When you see a star, you are literally receiving matter that was once part of that star, particles of light that began their journey in a nuclear furnace millions or billions of years ago. We are bathed in ancient light. It surrounds us always, this radiation from the past, this message from the cosmos. Most of it is invisible, shifted into wavelengths our eyes cannot detect. But it is there, filling space, connecting us to the universe in the most direct way possible. The Webb telescope lets us see more of this ancient light. It extends our vision into the infrared, where the oldest and most distant messages wait. It reads the cosmic story in wavelengths we could never perceive unaided. It makes the invisible visible, the unknowable knowable. And now, with the telescope's help, we have found something we did not expect. The impossible galaxies, the universe breakers, the signs that our story is incomplete. Let this finding be your lullaby. Let it sing you into sleep with its mystery and its promise. The universe is bigger than we knew. The story is stranger than we guessed. And we, tiny creatures on a small world, have been given the privilege of knowing this. Tomorrow, the sun will rise. The world will turn. Life will continue with its ordinary demands and distractions. But somewhere above, the golden telescope will keep its watch. Somewhere far away, the ancient light will keep traveling. And somewhere inside you, the wonder will remain. A quiet flame that needs only a dark sky and a curious heart to burn bright again. Until then, rest. Dream of stars and galaxies. Dream of light traveling across the void. Dream of the impossible becoming possible, the unknown becoming known. The universe is dreaming with you. The cosmos is at peace. Sleep well now, child of stars. The light will be there when you wake, ancient and ever patient. The telescope keeps watching. The galaxies keep spinning. And the story keeps unfolding, forever and always, into the beautiful unknown. Sleep well.